Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next few weeks, I'll be releasing sample questions from each of the 4 AP Physics exams to help students familiarize themselves with what kinds of questions are asked for the free response questions and how the AP exam will expect them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day for a number of reasons, and this video series is primarily intended for those students. AP Central lists the following types and number of free response questions students can expect to see on the AP Physics C Mechanics exam. First of all is experimental design, or with a lab-based component, and that's what we're focusing on in this video. And then the questions on the whole will assess all 7 of the science practices listed here. Today we'll be taking a look at the C Mechanics exam 2015 free response question number 3, which covered rotational dynamics and kinematics. A uniform thin rod of length L and mass M is allowed to pivot about its end as shown in the figure below. Part A. Using integral calculus, derive the rotational inertia for the rod around its end to show that it is mL squared divided by 3. So we're going to start with our general expression for rotational inertia as the integral of r squared dm, where dm is our differential little piece of mass, and r squared is going to be referring to the distance along the length of the rod from whatever place we call 0. So to do this, we need to figure out what is that dm. So let's start with an expression for the linear density of the rod, lambda, which is equal to the mass divided by the length. And so we can express the mass as this density times the length of the rod. And now we can see that our dm, little differential mass piece, is going to be equal to lambda dr, where dr is referring to sort of like that little differential location along the length of the rod from 0 to L. So that becomes our limits of integration. For our integral, I equals the integral from 0 to L of lambda r squared dr. And now we can evaluate that integral. Remember that lambda is a constant, so it comes out front, and we're just left to integrate r squared dr, which gives us r cubed over 3, which we will evaluate from 0 to L. So I will be equal to 1/3 lambda times L cubed minus 0, which is 1/3 lambda times L cubed. And now we can substitute back in mass divided by length for lambda, that linear density, times L cubed, and we finally get that 1/3 m L squared that we were supposed to get. So let's talk about scoring. And here we go. So we're going to get 1 point for a correct expression for dm. Hold, please. There we go. Our second point is going to come from correct limits of integration. And our third point is going to come from correctly evaluating the integral leading to, let's try that again. Got a little carried away writing the G. And I need pen, not highlighter. Oops, there we go. Leading to the answer ml squared divided by 3. So the rod is fixed at one end and allowed to fall from the horizontal position A through the vertical position B. Part B, derive an expression for the velocity of the free end of the rod at position B. Express your answer in terms of m, l, and physical constants as appropriate. So I'm looking at this and seeing that our rod has one position and one velocity at one point in time, and then it has a different position and a different velocity at a different point in time. So that suggests to me energy is the most likely approach. So let me switch up my pen color. Okay, so in fact, we are going to start with the rotational kinetic energy at A plus gravitational kinetic energy at A, and that will be equal to our rotational kinetic energy at B plus gravitational potential energy at B. Because, of course, the center of mass of the rod is changing position as the rod swoops down. So that's how we're going to think about gravitational potential energy. And there isn't any rotational kinetic energy at the start, so we just have gravitational potential energy, where the height of A is going to be the height of the rod above where it ends. And then when we get to point B, because our rod has come down and our center of mass has dropped, we have only rotational kinetic energy and no gravitational potential energy at B. So we can say 1/2 I times omega B squared. So now we need to think about the fact that, our rod went from this position to this position, and our center of mass of the rod went from here to here. So we can see that this height of A that our rod dropped is just going to be equal to half the length of the rod. So we also will need to substitute with our correct M, L, and other physical constants. So now we'll go ahead and replace the little m for general mass with capital M for the rod's mass. mg times L over 2. And then 1/2. And we just learned in the last part that our rotational inertia for the rod is 1/3 ml squared. And that will be times omega squared. I'm going to leave off the B subscript because there's only one angular velocity that we're going to worry about here. So we are going to need to remember that there's a relationship between tangential or linear velocity and angular velocity, because we've got to get that omega canceled out, because that's what we are finding the linear velocity of the free end of the rod, not the angular velocity. So we have to make a substitution. And so R, the radius of the path for this rotational motion will be equal to L. So we can say that omega is just going to be V divided by L. And so now we can make our substitution. And I'm going to write things just a little bit differently. 1/2 capital M times G times L equals 1/2 1/3 capital M times capital L squared over V divided by L squared. And I wrote it like this because now you can see really easily some things that are going to cancel, right? Those 1/2s are going to go away. We have a mass on both sides of the equation and everything is multiplied on both sides, so we can just divide by mass. And then also notice that the L squared from the moment of inertia is going to cancel with the L squared from the angular velocity squared. And so we are going to end up with G times L equals 1/3 V squared. And I'm going to go ahead and write this as V equals the square root of 3 times G times L. And so now we can talk about scoring. We're going to get 1 point for any expression for conservation of energy, which I'm just going to abbreviate COE, conservation of energy. We are going to have a point for a correct energy expression. I'm going to abbreviate energy, NRG. It's one of my quirky things. Correct energy expression relating gravitational potential energy to rotational kinetic energy. We get a point for correctly substituting. I'm going to leave off the correct because it adds stuff to write. For correctly substituting, L over 2 for the change in height. And then we're going to get our final point for using V equals R omega with R equals L to solve for the velocity of the end of the rod. An experiment is designed to test the validity of the expression found in Part B. A student uses rods of various lengths that all have a uniform mass distribution. The student releases each of the rods from the horizontal position A and uses photo gates to measure the velocity of the free end at position B. The data are recorded below. Part C. Indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration due to gravity g. Well, hey, we just saw in that last part, we had this expression. Oops, I'm trying to grab a new color. There we go. We just saw V equals the square root of 3GL, which is also the same as V squared equals 3GL. So that gives us a couple of nice clues of what we can use. So for one option for our horizontal axis, we could have length for horizontal and velocity squared for vertical. Another option would be to have the square root of length on the horizontal axis and velocity on the vertical axis. And also there was a note in the guidelines that each of the above axes choices can also be switched to yield a straight line. I like V squared equals 3GL. because I don't want to deal with square roots when I'm, dealing with a slope. I like this because this shows me really clearly that if I think about a linear relationship as dependent variable equals a slope times an independent variable, makes it really easy for me to see that my slope will be 3g. Spoiler alert. So use the remaining rows in the table above as needed to record any quantities that you indicated that are not given. Label each row you use and include units, which are shown on the next slide. Oh, and I actually forgot to tell you about scoring. Oops, let me erase that. And then scoring really quickly. This is going to be +1 for correctly identifying, again, I'm just going to leave off the correctly, for identifying a relationship between length and velocity that will result in a straight line. All right. So here's our data table again. I've gone ahead and filled in the quantities that we might need to calculate, and I've color-coded it with the blue for the v squared versus L relationship, and purple for if we want to do v equals the square root, well, v is related to the square root of L. Part D, we're going to plot the straight line data points on the grid below, which is the next slide, and clearly scale and label all axes, including units as appropriate. Draw a straight line that best represents the data. So here you see the plot of velocity squared versus length, which does in fact yield a straight line. We can always, oops, I lost my focus. There we go. Now I can put my straight line fit on my graph. So I used, instead of plotting by hand, which you would do on the exam, I went ahead and used graphical analysis. Oh, there we go. I lost my cursor. So I used, it's called Graphical Analysis. It's a free tool from Vernier. It's great for creating quick plots like this. So we're going to get 1 point for a correct scale that uses at least half the grid. So don't cram your data and your plot all in a corner. Spread it out. And you have to correctly label your axes, including units. So yeah, this and this down here, whether you write it in words or symbols, got to have labels with units. We're going to get a point for plotting data consistent with the quantities identified in the data table in Part C. And last but not least, our final point is coming from drawing a straight line consistent with the data in Part C. So you won't have a ruler on your AP exam, but you will have your question booklet alongside your answer booklet, and you can always close your question booklet and use its edge to have a straight line for drawing. A straight line. E part 1, using your straight line, determine an experimental value for G. So remember that what we saw earlier is that V squared equals 3G times L. So I'm going to say that my slope is equal to 3 times G. And the slope I got from my linear best fit was 25.77. So that equals 3G. And I got a value for G of 8.59 meters per second squared. And as far as scoring, I get one point, and I hate it when I lose. This orange is really hard to see on the white background, so it makes it really easy to lose track. 1 point for correctly. Again, I'm leaving off the correctly for calculating G using your slope. And finally, E part 2. Describe 2 ways in which the effects of air resistance could be reduced. There are a number of ways that air resistance could affect this data. So, a few that were suggested in the scoring guidelines are to do the experiment in a vacuum, use shorter rod lengths so that you have less length of the rod that has to cut through the air, so like fewer impacts with air molecules. You could use more massive or denser rods, or you could use a more aerodynamic shape for the rods. And your points here, you get +1 for an example that directly decreases the effects of air resistance. That's key. It has to directly decrease the effect of air resistance. And then your second point is for a second example. And I'm not going to write all of that. That directly decreases the effect of air resistance. So I hope you found today's demonstration of an experimental design question from the AP Physics C Mechanics exam helpful. If you have a video solution request for me to put on my YouTube channel, you can send it to physicsproblemrequests@gmail.com, but I won't be working on those until my AP series is over. If you would like some email assistance with a limit of 10 questions per academic year, you can reach me at freephysicshelpline@gmail.com. If you'd like to know more about my online tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics C Mechanics exam, and those materials include the released free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took the exams, and to see what the scorers for that year were looking for and how they decided to award points. If you have questions, you can reach me at brandyheflinphysics@gmail.com. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.